So for covalent network structures, like I said, the covalent part still means it's the same bonding. Okay, so this part isn't changed. Screen. Okay, so it's the same bonding, but i.e. We're sharing electrons between nuclei. But where the difference does come in is we know that a molecule is what? Discrete particle. Because we just made a whole bunch of them, didn't we? Okay, and they turn out to be like blobs. They're three-dimensional structures that have a beginning and an end. But with our network structures is an ongoing crystal. So our network is an ongoing crystal lattice. Where have we heard about crystal lattices before? With ionic bonding. Okay, but this doesn't have ionic bonding. But it does form a crystal lattice. And what do we need for it to be ionic bonding?
Ions.
Ions. And they're generally formed between what? Metals and non-metals. Whereas our covalent network structures are forming an ongoing crystal lattice by sharing electrons between the nuclei, and these are with non-metals. Okay, they're non-metals. Now within our covalent network structure, there are two types. Of course, just to make things a little bit more complicated. We have two-dimensional. What's another way of describing something that's two-dimensional?
Flat.
Flat. And we also have three-dimensional. Okay, and those ones are obviously not flat. The one that we talk about for the two-dimensional covalent network structure is graphite. What do we know that graphite is made from? Anyone know what graphite's made from? It's made from carbon. And we can also make a three-dimensional crystal lattice from carbon. And what do we call that?
Diamond.
Diamond. That's right. And so the reason why we can see that carbon is quite versatile in the way it can bond is because it's got these 4 valence electrons that allow it to bond with itself in these sorts of ways. Now, let's have a little bit of a closer look at graphite to start with as our example of a two-dimensional network structure. just said how many valence electrons carbon has. Do you remember how many it was? 4. So if we look at what happens in graphite, what we end up with is a sort of hexagonal arrangement. So each carbon must have 4 bonds. And we are joining them together in a hexagonal shape. So what can you tell me about what's wrong with that? So it's only got 3 bonds. And so with graphite, even though the carbon has 4 valence electrons, each carbon bonds to 3 other carbons, atoms, in this hexagonal arrangement, and that last valence electron is delocalized. Okay, so we end up with these flat sheets of carbon. That they can just go on and on like this. And if so, this is looking down. So this is. You need to be able to draw this kind of diagram. But if we look from the side on, what we have are flat layers like this, and in between them are our delocalized valence electrons. In fact, they can travel through the layers as well. Now, what do you think this is going to do for the properties of graphite?
It's going to be able to conduct electricity.
Yeah, so it's a non-metal, 3-dimensional, covalently bonded structure that can conduct electricity and heat. Now, these delocalized valence electrons, sort of between the layers, mean that the layers aren't very firmly bonded to each other. So that within the layer, these bonds here are strong. Within the hexagonal bonds, these are strong bonds. But these are only weak forces of attraction, and so that allows the layers to slide across each other. Okay, so the layers slide. And this is why graphite can be used as a lubricant. So sometimes, you know, if the key is starting to get stuck in the door, you can put a bit of graphite powder in the lock, and that will free it up, and the key doesn't stick anymore. And you would use that somewhere where you don't want to use a grease or that other kind of lubricant where it's going to gum it up and cause more trouble. It actually still has a high melting and boiling point because of these strong bonds. fact, it's got a high melting point. It won't boil. It sublimates. What else do we want to say about it? Forgotten something? There's one other property that we haven't talked about. What do you think graphite is going to look like?
Wouldn't it be like kind of flaky? Like a rock?
It does look like a rock. You can't necessarily see the flaky bit, but you can see something else.
It'll be a little bit shiny.
It's a little bit shiny. Why is it a little bit shiny?
It's the electrons, like self-detonate.
Yeah, because we've got these delocalized valence electrons. Give it that a luster. So it conducts heat and it conducts electricity, and it's got a high boiling point and it's got this shiny luster. Is it a metal? Why isn't it a metal? Why are we saying it's not?
Are they not ions? Are they atoms instead? Is there a difference there, or?
There is a little bit of a difference there. They're not ions, no.
Has it got something to do with carbon being a gas?
Carbon isn't a gas,
Not a gas.
no. But carbon is something else.
Liquid?
No,
Metalloid? Is it
it's not even a metalloid. It's just a non-metal. Okay, we can't have metallic bonding unless the element is a metal. Carbon is a non-metal. Now, under normal circumstances, standard conditions, carbon is a solid. Yeah. But we do see it in gases like carbon dioxide and carbon monoxide, etc. But that's then with it bonded to something else in a compound. But just the element carbon is a solid at room temperature. But yeah, this can't be metallic bonding because carbon is not a metal. Does that make sense? It's sort of a fundamental thing that it can't be. But it certainly in this arrangement, in this bonding arrangement, it has some properties that are similar to gas.
If it does have all these properties that are similar, why is it considered a metal?
Why isn't it?
Yeah. Like what are we actually saying? Like, why is it being classed as a non-metal when all of these things point towards the fact that it's possibly a metal?
Well, because I guess if we think about carbon, this is only one way that carbon bonds. Every other way that carbon bonds, it's clearly a non-metal. But not only that, as you rightly said, what we don't have are carbon cations with loosely held valence electrons, which is the other property that we would need for it to be a metal. This is not malleable. It's not ductile. And so it's got some properties in common with metals, but you cannot draw it out into a wire, and if you hit it, it will just sort of break apart. It's not going to change shape because these layers are brittle. Even though they're strong, these layers here are more brittle than a metal. You see, you hit them and they'll break. Now one layer, this one layer here, has a separate name. It's not just graphite. Has anybody heard of what one layer of graphite is called? No?
Is it a sheet?
Well, it's got a name. It's actually called graphene. It's just one layer. And look, I think it was 10, 15 years ago, some scientists who were studying graphite won the Nobel Prize for isolating a layer of graphene. It hadn't been done before. And they did this by getting a lump of graphite and sticky tape and peeling. They were just peeling layers off, and they managed to peel off one layer, and got the Nobel Prize. Because from this we've been able to then expand on graphene, and we can buckyballs. Have you heard of buckyballs? No? Good. This is a buckyball here. So this is just all the black balls on this are carbon atoms again, and the bonds of the blue sticks between them, and it looks a lot like a soccer ball because it's the same bonding arrangement, and this is made from one layer of graphite, the graphene rolled into a ball. These are very special. You can also make them into tubes, and they're semiconductors because you can lock the electrons on one side. So the electrons could all be on the outside, or they could all be on the inside of the ball, or they can be transmitted along a narrow tube. And if you imagine that you're making a tube and it's only atoms wide, it's very narrow, and that's powerful for doing things on a nano scale. There are health issues around them though, so they're not actually that good for you. But yes, buckyballs. So their proper name are Buckminster fullerenes. And the buckyballs are just one kind of Buckminster fullerene, but all based off a layer of carbon in this graphite arrangement where we've got 3 bonds of the delocalized valence electron. Okay, now I want you to have a go at drawing yourselves a diagram